Hi there, this is our video lecture for the course ENSC113. This is a differential equation course. Okay. In this video, what I would like to do is to give you an overview of what differential equation is all about. Um, and also I would like to give you uh, to give you a perspective about the difference of these differential equations to the other previous math courses that you have already taken up. Okay, so to start, recall that in your first math courses is probably it's the pre-calculus. Okay, so from the word itself, it's pre, meaning before you taken up, before you take the course in calculus, you have to have a solid foundation on um, algebra, analytic geometry, okay, analytic geometry, and also trigonometry. Trigonometry. Okay, so that's why when you had when you took this course, yeah, you would encounter topics on algebra and analytic geometry, which relates the equations to the graphs. Okay, so this is just purely equations, and this one relates to the graph, and then this one relationship of the angles and the sides, right? But it's it's actually oriented toward the topic on functions. Okay, because after all, the um, the course in calculus uh, is all about functions, differentiable functions. Okay, so when I say functions, what is it? So basically, functions um, is an equation relating relating two or more variables. Okay, so we are relating two or more variables, and mathematically, it's expressed as um, or the basic expression is y is equal to f of x. All right. Okay, so as I have said here that functions are equations that relates two or more variables. Okay, so in engineering applications, there could be more than two variables. But of course, if you have more variables, then the mathematical operations would be complex. Okay, so right here we have this basic expression, which is just y is equal to f of x. So y is one variable and the x is another variable. Okay, so in this equation, or in this expression, what that means is that the x is the independent variable, and the y is the dependent variable. So what that means is that y depends on whatever value uh, whatever value of the x. Okay, so for example, y is equal to x squared plus 1, or y is equal to 2x, or y is equal to sine 2x, or things like that. Okay, so whatever input or whatever the value of x, okay, that's if you input that in this equation, and that's going to be the value of y. So something like in it's sometimes this function is drawn as a something like a machine, right? So let's say you have an input right here, and then you have an output. Okay, so let's say this is a function machine. So if you input x, right? So if you input all the x values, then it will produce okay only one y values, right? So let's say if you input 1 right here, and if our function is x squared plus 1, so that's going to be 1 squared, so 1 plus 1, so this will be 2. Okay, so that's the mathematical side. But for us engineers, what we actually want is to relate these mathematical expressions in terms of the physical phenomena, or physical situations. Okay, because after all, we are um, we encountered situations like, for example, heat transfer, or fluid mechanics, or even the strength of materials, okay, and things like that. We use mathematics to describe those situations. Okay, so let's discuss here some functions uh, that we will encounter in engineering. Okay, so first and foremost probably is the velocity. Okay, so velocity usually, it's a function of time. And by the way, when say velocity, velocity is just simply the change, right? The change in in position over the change in time. Okay, so what that means is that, for example, we are in this 3D space, okay, x y z. Okay, and let's say this is the position. So let's have a motion purely in one dimension. So let's say purely along x. So let's say the first position is, I'm right here, and then after some time I change the position to this x value, right? So this is x1, this is x sub 2. Okay, so meaning that the rate of change of position, okay, so how fast am I changing my position with respect to time, how fast, so that's gonna be my velocity. Okay, so that's why sometimes it's expressed that velocity as a function of time. Okay, so it's also common though in fluid mechanics that velocity is not just a function of time, but it's also possible to have a velocity as a function of space, right? So velocity as a function of x, y, and z. Okay, so what that means is that, for example, this is my first position, right? Arbitrary position, and it has a value of x, y, z. And then after some time, it changes to this position, so another value of x, y, z. Okay, so that's why in uh, if that is what we want to describe, then that means that velocity can vary in x. Okay, so it can vary in x, in y, and in z. Okay, another example of functions is viscosity. So vi- viscosity, the value of viscosity is a measure, or something like a measure of resistance of fluid flow. Okay, so as the fluid flows, right, for example, in a conduit, so as the fluid flows from this point to this point, there there's actually a resistance, okay, especially especially in the boundary, so between the fluid layer and the solid and the solid wall. Okay, so in that case, it's often expressed. Sometimes it's expressed in empirical relations, that viscosity is a function of temperature. Okay, so what that means is that the viscosity, or the resistance, if it is high temperature, then what's going to happen in the viscosity, and if it is cold, let's say if it's cold, then what's going to be the resistance. Okay, so you would notice that actually when you're heating a substance, uh, right? So when you're heating a substance that, let's say, a something like a solution with sugar and things like that. Okay, so when you're heating this, you would notice that it is easier to it is easier to to steer, right? But if it's cold, if it's cold, then it's gonna be harder. Okay, so what that means is, is simply that the viscosity is a function of temperature. Okay, another example function is the heat. So the typical or the basic expression for heat flow is, heat flow for conduction is Ka delta T all over delta X. Okay, so we can say right here, or we can also have an expression like, for example, heat is a function of temperature. But what I would like to focus right now is this term. Okay, so this term, this K, this is called the thermal conductivity. Okay, so how much heat does a material be able to conduct? Okay, because some materials are insulative in nature, so meaning it doesn't allow much heat to conduct, or it retards the flow of heat. So in heat transfer course, we assume that this is constant, right? For example, for a specific material, like for example polystyrene, then what's gonna be um, the value, and it's taken as a constant. Okay, however, for some materials, like for example liquids or gases, this K is a function of temperature, or sometimes K is a function of pressure. Okay, so what that simply means is that this K value depends on what temperature that you have. So you would notice, like, maybe an empirical equations like A plus B, B times T, right? This is just an example. I'm not sure actually if I don't remember exactly what's gonna be the relationship, but the point right here that I'm referring about is that if you see this equation that K as a function of T, then you have these equations. So A is whatever constant, or B is also another constant, and this is just a function. Okay, so A plus BT. So that means that the value of K would depend on the value of whatever temperature, or it changes, or yes, something like that. It's a variable. Okay, so going back to our basic definition, is that this X, this T is our independent variable, and this value right here, that's our um, independent variable. Okay, so you have learned that there are many types of functions, right? Okay, types of functions. And what that means is that there are functions that are constants, so meaning it doesn't change. Okay, and there are functions that are linear. And if we try to write here, we have this, right? So for example, we have this, let's say the position, the graph of position and time. So if it's if constant function, then that means the that this is our function, our line, right? Or our curve, our function itself, right? So that means that the graph of position is not changing. Okay, so that means that the object is not moving. It's not actually changing its position from time one. Let's say we have this time one. Okay, from time one to time two. So it's not changing its position. And for linear functions, the graph is right, the graph is like this, and our function is like that. Okay, so that means that if this is my initial position, let's say this is time one, or at time one, during time one, this will be my initial position S1. And then after some time, it was found out that my position changed. Right, this is S2. Okay, so the graph of linear functions is basically a line. And there are also functions like a polynomial function. So instead of having a degree one polynomial, instead of having a degree one equations, we have degree two and higher. Okay, so if that's the case, what it looks like is this, right? So for example, we have something like a quadratic equations. So what that means is, let's say at time one, right? At time one, this is my position, and at time two, this is my position. Okay, so what's the difference between these polynomial functions and the linear functions? Is simply the rate of change. So how does it go from point one to point two? Is this has this curve right here. So at first it's not accelerating, and then uh, I mean the slope, right? The slope, which is the velocity, is actually changing. The velocity is let's say there is an acceleration that's going on in this curve. But for this one, for linear functions, it's just a constant slope, right? It's a constant velocity from point one to point two. So that's gonna be the difference. Okay, and there are also functions like, for example, um, exponential functions, exponential, and also logarithmic functions, and also trigonometric functions, which has they have also characteristics in terms of the graph. Okay, trigonometric functions. Okay, for the exponential functions, it's somehow the same, or is somehow the same as this quadratic, except that the the rate of increase is much faster. It's something like this. So it has a much higher rate of increase. Okay, so that's the characteristics of exponential functions, and there are also functions like sine functions. So for example, the voltage and the voltage waveform in electric circuits, right? So we have this waveform, voltage, and a current waveform that just simply means repetitive. Okay, so cyclic or something like that. Okay, so those are the functions.